Hi everyone, I am Lin Clark and I make code cartoons. I also work at Mozilla. I work in the emerging technologies group there. So that's things like the Rust programming language, and Servo, which is a super fast browser engine, and WebAssembly, which is what I'm going to be talking about today. Now, if you are a JavaScript developer, I don't know how many of you are JavaScript developers. Okay, we have we have a number of you in here. Okay. So you may have noticed that there's a lot of hype about WebAssembly right now. People are talking about how blazingly fast it is and how it's going to completely change the way that we do web development. But a lot of these conversations don't go into details about how WebAssembly will actually make things faster. And I know when I hear claims like this, when I hear this kind of rhetoric, but I don't hear anything to back it up, I get really skeptical. So in this talk, I want to help you understand not just that WebAssembly is fast. I want to help you understand what it is about WebAssembly that makes it fast. But first, what is WebAssembly? WebAssembly is a way to run programming languages other than JavaScript in web pages. In the past, when you wanted to run code on a web page, your only option was JavaScript. So if you wanted to change the DOM in the response to an event, or you wanted to run a calculation, you'd have to be using JavaScript to do that. But with WebAssembly, other languages will be able to do these things too. So when people say that WebAssembly is fast, the apples to apples comparison is with JavaScript. But I don't want to imply that you're either going to be using WebAssembly or you're going to be using JavaScript. We actually think that people are going to be using these things together hand in hand. But it's useful to compare these two. It's useful to compare WebAssembly and JavaScript so that you can understand what this improved performance could mean for the web. In order to understand this, let's take a look at a little bit of performance history on the web. JavaScript was created in 1995 and it wasn't designed to be fast. And there are a number of features in JavaScript that make it really hard to make it fast. Things like the dynamic types, where you have a variable that could be a string or it could be a number and you don't know until you're actually running the code which it is. And it can even change while you're running the code. But these features are also what make it easy to get up and running with JavaScript quickly and what make it easy to write JavaScript quickly. So JavaScript developers just accepted that their code would be running a little bit slower for this ease of use, this ease of development. For the first decade of JavaScript, this was true. JavaScript was pretty slow in browsers. And then the browsers started getting more competitive. In about 2008, this period called the performance wars starts, where the browser vendors started making JavaScript run much, much faster in their browsers. The technique that they used to do this was introducing JIT, or just-in-time compilers, into the JavaScript engine. And I'll explain more about what this is later. But for now, let's look at the impact that these JIT compilers had. With the introduction of these JITs, you see an inflection point in the performance of the web. All of a sudden, the execution of JavaScript was going 10 times faster. And these performance improvements continued over the next decade. With this improved performance, you start seeing JavaScript being used for things that you wouldn't have expected. Things like Node and Electron. And these new applications are possible because of this improved performance. It's because of this inflection point that happened in 2008, 10 years ago, that we see the kinds of JavaScript applications that we see today. So that's why it's interesting that we may be coming to another one of these inflection points in the speed of code running on the web with WebAssembly. And this is where I need to actually start backing up what I'm saying with some details. To do this, I need to explain a little bit about where JavaScript spends its time today. So here's a diagram of where the JS engine spends its time for a hypothetical app. This isn't showing an average. Any particular app that you have would look different from this. But we can use this to build up a mental model. You may have seen diagrams like this one before and be confused why my categories are a little bit different, why I have fewer categories. For this one, I've combined some of the categories so that it's easier to talk about them and reason about them. So these categories are parsing, compiling and optimizing, re-optimizing, executing the code, and garbage collection. Now let's look at what this diagram would look like for WebAssembly instead of JavaScript. You'll notice that some of the bars are shorter and some of them are missing completely. In this talk, I want to explain to you what it is about WebAssembly that changes how long these tasks take. But first, let's look at where the JavaScript engines would be if they hadn't introduced the JIT compiler. In the early days of JavaScript, the diagram would have looked more like this. There was parsing, running the code, and garbage collection. What made that execution bar shorter, what made it run faster, was the introduction of the JIT. So it was by adding some overhead, by adding that compilation overhead, that you could reduce the amount of time that you spent running the code. Now with WebAssembly, we want to make these bars even shorter. In order to see how to do that, we're going to need to dive more into what exactly it is that the JIT does. So I'm going to run through a very quick crash course on JIT compilers, and this is a general overview. Each of the engines in browsers today have different architectures, and those architectures have changed over time and are currently changing. But most of this applies to them right now. This may be review for some of you, but it's going to be quick. I just want to make sure that we're all on the same page with this. When you're developing, you have a goal and you have a problem. The goal is you want to communicate to the machine what you want it to do. And the problem is that you speak a human language and the machine speaks a machine language. Even if you don't think of JavaScript being a human language, it really is. It was designed for human programmers to be able to program it. It's designed for the way that humans think. I think of this like the movie Arrival, where you have humans and aliens who are trying to talk to each other. It's not as easy as just translating word for word from the alien language to the human language, though, because the two groups have two different ways of viewing the world. And that's true of humans and machines, too. I'm going to explain more about the differences in the way that we think later, but let's look at the process of actually translating. In programming, there are generally two ways to translate. You can either use an interpreter or you can use a compiler. With an interpreter, the translation happens pretty much line by line, on the fly. A compiler, on the other hand, doesn't translate on the fly. It takes some time, it sits down ahead of time and writes out its translation. And then it hands off that translation. There are pros and cons to each of these ways of handling translation. For an interpreter, some of the pros are that it's quick and easy to get up and running. You don't have to go through the whole compilation step ahead of time. You can just start running your code. So an interpreter seems like a natural fit for something like JavaScript, where you want that developer to have that immediate feedback loop, that immediate experience of seeing what their changes have done. And that's why in the beginning, browsers used JavaScript interpreters. But the trade-off is, if you're in something like a loop, where you're running the same code over and over and over again, you have to do that translation over and over and over again. The compiler has opposite trade-offs. It takes a little bit of time to start up, because it has to go through that compilation at the beginning, but then you don't have to run that translation cost. You don't have to run that translation over and over and over again in loops. Another difference is that interpreters are running at the same time as the code is running. They're doing their work during runtime. So they can't take additional time to think about how the machine thinks and what the best translation is for the machine. But since compilers are working ahead of time, they can take that additional bit of time and think about what an optimal version of this is for the way that the machine thinks. This is called optimization, when it takes that time to think about how the machine thinks and how it can make the code run faster for the machine. To get the best of both of these worlds, browsers started mixing in compilers. They added this new part to the JavaScript engine called a monitor or a profiler. The monitor watches the code as it runs. It keeps track of things like how often a particular part of the code is run. And at first, the monitor just runs everything through the interpreter. If the same function is run a few times, that function is warm. And when a function gets warm, the JIT sends it off to be compiled by a baseline compiler. The baseline compiler is going to start making a compiled version of the function, and it's going to do this in chunks. Each operation in the function is going to be compiled to one or more stubs. So for example, the += sign is an operation. So the compiler would create a stub for that. And that stub would be specific to whatever types were on either side of the plus equals. So if you had two integers on either side, then that compilation would be specific for integers. If the monitor hits that operation again with the same variables, so if you hit it again and it has integers on both sides again, then it can just take its compiled version and use that. And if not, it can create another stub for whatever types are on either side of the plus equals. And then it will store that other stub too. As the code runs, more baseline stubs will be filled in for the different operations in this code. So that saves on the translation time and helps speed things up. But like I said, there's more that a compiler can do. It can spend some time on figuring out the most efficient way for things to run on the machine. It can take time to make those optimizations. A baseline compiler will make some optimizations, but it doesn't want to take too much time while the code's running, so it won't make all of the optimizations that it could. However, if the code is really hot, if it's being run a whole bunch of times, it can be worth taking that extra time to make more optimizations. So when a part of the code is very hot, the monitor will send it to the optimizing compiler. And this will create another even faster version of that code. In order to make the faster version of the code, though, the optimizing compiler needs to make some assumptions. For example, if it can assume that all objects that are created with the same function have the same shape, that is, that they have the same properties, and those properties have all been added in the same order, then it can cut some corners and make things go faster based on that. The optimizing compiler uses the information that the monitor's been gathering to make these guesses about how the code works. But sometimes, even if something's been true every other time that function is run, that doesn't mean that it's going to be true the next time. In JavaScript, you don't have those guarantees. You could have 99 objects that are the same shape, and the 100th is different. So the compiled code needs to check before each time it runs to see whether or not the assumptions are valid. And if they are, then it uses that compiled code. But if not, the JIT assumes that the assumptions that it's made aren't working out, and so it throws out the version of the code that it's compiled. And then execution goes back to the interpreter or baseline compiled version. This process is called de-optimization or bailing out. Usually, optimizing compilers make code faster, but sometimes they can cause unexpected performance problems. If you have code that keeps getting optimized and then the JIT has to keep bailing out on it, it's going to run slower than it would have if it just went through the baseline compiler. So a lot of JITs will keep track of how many times they've tried to optimize this code, and if they've tried too many times, they'll mark it as not even worth trying again. So that is the JIT in a nutshell. Code starts off running in an interpreter, and a monitor collects information about it. Then that monitor will send code off to be compiled depending on how often that part of the code is executed. Now that we understand more about what the JIT is doing, let's look at ways to help this JS engine go faster. One way is to get rid of some of the overhead. We could move some of the overhead, like compiling, ahead of time. But in order to do that, we would need to get rid of the dynamic types. If you're going to be optimizing ahead of time, you're not going to be running the code to see what types are coming through. So these dynamic types that can change at runtime are a problem. But I already suggested that that was part of what made JavaScript successful. The fact that you had these dynamic types so that developers could just get up and running quickly. Why would we want to change something that made JavaScript successful? I want to be clear that we don't actually have to change anything about JavaScript in order to get the advantages of WebAssembly. But there is a change that is already happening in JavaScript that we can take advantage of. And that is the move towards modularity. Over the past few years, both with NPM and with the ES 2015 module spec, JavaScript has become a much more modular language ecosystem. The nice thing about modules is that they provide boundaries. You don't actually need to know about what's going on in code that you depend on. So these modules, they could be compiled ahead of time using a language that doesn't have these dynamic types, and it wouldn't affect how you code. So take, for example, React, which has a bunch of different consumers. And the React core team has already been working on performance of their reconciliation algorithm. An option for them could be to rewrite that reconciliation algorithm in a language that compiles to WebAssembly, something like C. As long as they keep the API the same, consumers of React wouldn't actually notice that, except that when they update the code, they might notice a performance improvement. That's the only thing that they would notice. So this is what WebAssembly does. It makes it possible for library authors and application developers to code in languages that are more consistently performant, but then to have the code run on the web in the same way that JavaScript would, and to integrate and communicate with existing JavaScript. This means that you'll be able to benefit from WebAssembly without having to understand it or why it's fast. But I think it's more fun when you do understand those details, so I'm going to go ahead and walk you through how it is that WebAssembly works. To do that, I'm going to have to do another really quick crash course, this time on assembly and compilers. I talked about how communicating with the machine is like communicating with an alien. I want to take a look now at how that alien brain works, how the communication that is coming into it is parsed and understood. There's a part of this alien brain that's dedicated to doing the thinking. Things like adding and subtracting and logic happen here. There's also a part of the brain near that which is short-term memory. And these are pretty close together. They're encapsulated in one part of the brain. And then there's some longer-term memory. These different parts have names. So the part that does the thinking is called the arithmetic and logic unit, and that it's abbreviated the ALU. The short-term memory, those are called registers. And that's all encapsulated in the central processing unit. And then the longer-term memory, that's random access memory. And each one of these registers would have a name, which will make it easier for you to identify what the brain should be thinking about. The sentences in machine communication are called instructions. When one of these instructions comes into the brain, it gets split up into different parts that mean different things. The way that this instruction is going to be split up is going to be very specific to the wiring of this brain. For example, this brain might always take the 4th bit through the 10th bit and pipe that in to the ALU. And the ALU will figure out, based on what's a 0 and what's a 1 here, exactly what it needs to do for this instruction. So it'll figure out that it needs to add 2 things together. So this brain would then take the next 2 chunks, and that would help it figure out which 2 things it needs to add together. You'll see that I've been adding little notes above the code here. This makes it easier for us as humans to understand what's going on in this instruction. And that's actually what assembly is. It's called symbolic machine code. It's a way for humans to be able to read this machine code. You can see here that there's a one-to-one relationship between the machine code and the assembly code for this machine. And something you may have figured out from this is that you have a different kind of machine. There's a good chance that you'll have a different kind of assembly for that machine. Anytime you have a different architecture and machine, there's a good chance it's a different assembly. So we're not talking about the target of our translation being one assembly, being one machine code. It's many different kinds of machine code. Just as we speak different languages as people, machines speak different languages. So if we were talking human to alien translation, you may be going from English or Russian or Mandarin down to alien language A or alien language B. In programming terms, this is like going from C or C++ or Rust down to x86 or to ARM. If you want to be able to go from any one of these high-level programming languages down to any one of the assembly languages, you're going to need to create a whole bunch of different translators to do that translation. But that would be pretty inefficient. So what most compilers do is they put at least one layer in between. The compiler will take this high-level programming language and compile it down to something that's not quite as high-level, but also isn't working at the same level as machine code. And that's called an intermediate representation. So the compiler will go from any one of these higher-level languages down to the intermediate representation, and from the intermediate representation to any one of the assembly languages. The thing that goes from the higher-level programming language and translate it to the intermediate representation is called a front end. And the thing that goes from the intermediate representation down to any one of these assembly languages is called a backend. So now, where does WebAssembly fit in this picture? You may think that it's just another one of these target assembly languages, which is kind of true, except that each one of those languages corresponded to a particular architecture. But when you're delivering code to be executed on somebody else's machine across the web, you don't actually know what machine they are running on. So WebAssembly is a little bit different than usual assembly. It's a machine language for a conceptual machine, not for an actual physical machine. Once the browser downloads the WebAssembly, it can make the short hop between the WebAssembly code and the actual assembly code for that machine, for whatever machine it's running on. Let's walk through the tools that the developer of a library like React would use to make their code WebAssembly. The compiler toolchain that's had a lot of work put into it is called LLVM. And there are a number of different front ends and back ends that LLVM can use. So if we wanted to go from C to WebAssembly, we could take the Clang front end, and that would go from C to LLVM's intermediate representation. And then LLVM could do some optimizations, because once it's in LLVM's intermediate representation, it understands it. So it could do some optimizations for us. Then there's a backend that's currently in progress in the LLVM project that would go from the LLVM intermediate representation to WebAssembly. Like I said, it's currently in progress. You might not want to use it until it's fully finished. In which case, you can use a tool called Emscripten that has a fully functioning backend to go to WebAssembly. It uses a fork of LLVM under the hood. And even after the LLVM backend is done, you may still want to use Emscripten because it can pack in some helpful libraries. Things like a file system that works on top of IndexedDB. But regardless of whether or not you're using the LLVM backend to get there or you're using Emscripten to get there, the end result is a file that ends in .wasm for WebAssembly. This is the WebAssembly module that can be loaded in JavaScript. Right now, the way that you load it in JavaScript is a little bit complicated. We're working on making it easier to do that. We're actually working with the folks on the Webpack project, and other module loaders are also working on WebAssembly support. Plus, as the browsers have support for modules built in, the ES 2015 module spec built in, then WebAssembly will be able to use that too. So it should be as easy as loading a JavaScript module. But when I say that, I need to add a caveat. Even though loading the WebAssembly module should be the same as loading a JavaScript module, working with it is slightly different. So let's say that you're calling a WebAssembly function from JavaScript. Here's the JavaScript function, and here's the WebAssembly one. It was written in C. Functions in WebAssembly can only take WebAssembly types as parameters, and at the moment, that's numbers, so integers and floats. So that's different from regular JavaScript modules. The same restriction also applies to the return values from WebAssembly. What if you want to return a string, though? You can't do it. For any data types that are more complex, you need to put them in the WebAssembly module's memory. So this memory is just an array buffer. It's just a JavaScript array buffer. It's a JavaScript object that simulates the heap. The integers that get passed back and forth can be used as kind of like pointers into this heap. So then the C code can use that to write to that array buffer. It can put bytes in there as if it were a memory address. And then the JavaScript can use that number to figure out which index to pull the data from. Now, it's likely that anybody who's developing a WebAssembly module for web developers to use is going to put a wrapper around this module so that JavaScript developers don't need to understand how this memory works. But it helps understand some of these performance characteristics. What I want to do now is go back to this diagram and look at why WebAssembly is faster. So first off, this isn't shown in the diagram, but it takes less time to download WebAssembly than it does JavaScript for the equivalent JavaScript because it's more compact. It was designed specifically to be compact, and it can be translated into a binary form, which makes it even more compact. Even though gzip JavaScript is pretty small, the equivalent code in WebAssembly is still likely to be smaller. Parsing takes less time than JavaScript too. So JavaScript needs to be parsed from the source into an abstract syntax tree, and then it's usually converted into an intermediate representation called bytecode, which is specific to whatever JavaScript engine it's running on. WebAssembly is already a bytecode. It just needs to be decoded from the binary version. And decoding is faster than parsing. Compiling takes a lot less time because a lot of it has been done even before the file has been pushed up to the server. And plus, the compiler doesn't have to compile multiple stubs for those dynamic types. And you don't get into these optimize and de-optimize cycles that you did with the JIT because you're not making guesses about what the types are. You already know what the types are. Running your code is fast because many of the optimizations that the JIT had to make aren't necessary. And WebAssembly itself provides instructions that are just faster. So because human programmers don't need to program it directly, it can be optimized. The designers were able to create a language that's closer to how the machine thinks. Depending on what kind of work your code is doing, these instructions can run anywhere between 10 times faster and 10% faster and 800% faster. And as for garbage collection, at least for now, the languages that are supported use manual memory management. Now this is likely to change, and I'll explain a little bit more about that later, but for now you don't need to worry about garbage collection. So what's the status of WebAssembly? In late February, the browser vendors announced that WebAssembly was ready to ship on by default in the browsers. And we started shipping it on by default in Firefox the next week. And then Chrome did the same the week after. And it's currently in preview versions of both Edge and Safari. With this, developers can start shipping WebAssembly code. And for earlier versions of browsers that don't have this support, you can ship down Asm.js, which was a precursor to WebAssembly, but it's fully JavaScript, so any JavaScript engine can run it. What's in browsers is the MVP, the minimum viable product. Now this doesn't contain all of the features that the community group wants, but with it, WebAssembly is reasonably fast and usable. However, it should get even faster in the future through a combination of fixes in the engines and new features in the spec. For example, a fix that needs to happen in Firefox is that currently calling a WebAssembly function from JavaScript is slower than it needs to be. That's because it has to do something called trampolining. Instead of the JIT knowing how to directly call that WebAssembly function, it has to transfer control, and it uses a setup function to do this. This is a lot slower than it would be if the JIT just knew how to handle it directly. Now, slower is relative. We're only talking nanoseconds here. So you won't notice this overhead if you're taking a big chunk of work and passing it off to the WebAssembly module. But if you have lots of communication where you're calling functions back and forth, then you could potentially notice this overhead. So that's one example of the kinds of fixes that you'll see in engines. As for the spec, there are a number of features. Future features. One that's expected reasonably soon is threading. So one way to speed up code is to run the code in parallel at the same time. But this can sometimes backfire because the overhead of communication between threads can take up more time than the task would have if you just ran it sequentially. But if you can share memory between threads, that reduces the overhead. So to do this, WebAssembly will use JavaScript's new shared array buffer, which is shipping in browsers soon. Once that's in place in browsers, the community group can start specifying how WebAssembly will work with it. Another feature that needs to be standardized is direct access to the DOM. Currently, there's no way to interact with the DOM directly. This means that you can't do something like element.innerHTML from WebAssembly. Instead, you have to go through JavaScript to set the value. And the community group is currently working on adding this direct DOM access. One last feature that a lot of folks are looking forward to is integration with the browser's garbage collection, the built-in garbage collector. Today you can ship down your own garbage collector with your code if you want to, but that's kind of hard to get right for a few reasons. But the community group is working on making it possible for these WebAssembly languages, the languages that compile to WebAssembly, just to use the browser's built-in garbage collector, which will make it a lot easier. Unfortunately, that's all I have time to talk about, so I'll have to wrap this up. But I do want to say thank you to somebody who gave me a fantastic technical review on this, Luke Wagner. He's the person who came up with the way to make types work in Asm.js, which was the precursor to WebAssembly. And he also did a lot of the work to push WebAssembly forward. So thank you to Luke, and thank you all for listening. Thank you all. I think Sandra said that we had planned some time for Q&A. So how much time are you thinking? Like till 6:30 or? Okay, 5 minutes for Q&A. Are there any questions? I have projectiles that I can throw at you if you ask questions.
Right, so one feature that comes to my mind immediately when talking about threading and inter-thread communication is asynchronicity and how it could be handled with these background threads. Because you mentioned that you actually have shown an example how functions can return values, but what if you're actually running some asynchronous C or C++ code that should issue a callback to the JavaScript code? Is that even envisioned in the specification, or has that not been considered for a WebAssembly?
I think that I would need you to walk me through an example of what you're thinking of, so maybe we can touch base after the Q&A, the general Q&A.
Okay, well, I actually meant like, can you call JavaScript functions from C and enable asynchronicity, like callbacks from C to JavaScript?
Yeah, you can call WebAssembly functions from JavaScript and JavaScript functions from WebAssembly.
Oh, that's cool. Thanks.
Yeah. Oh, and you get projectile. Okay, there we go. Anyone else? Go ahead.
Okay, so basically as a typical front-end designer, I'm really scared about C stuff and C++ and all these things. But basically, I want to ask, there were lots of words like potentially, maybe, in some cases in your speech, and I want to ask, in your opinion, where do we want to use WebAssembly? Like, where is that the thin layer where it could be good for our code, and where is the other side where we are adding a new level of abstraction level, and it would be totally enormous?
That is a good question. I actually gave a talk at React Europe last week that kind of went into a little bit of that, because I think that the best opportunities for using WebAssembly is in libraries like React, where you have a core team that already knows a lot about, like they already know how to write C and stuff like that. I don't actually think the best opportunity is teaching front-end developers how to code in C. But they've actually been talking about the possibility of making tools where they could even compile, and this is further future, where you could take JavaScript and actually find a way to compile it to WebAssembly. Now, there's a lot of question marks there. So as much as my talk had possibly, maybe, you'd have even more possiblies and maybes in a talk about that stuff. But I think that for now, the place where you want to have it is in a library like React. In the future, you might see it actually being used by more application developers rather than framework developers if we make the tooling good enough. Any other questions? Yes.
You show that the support for WebAssembly is already going to all those browsers. Do we also speak about mobile? What about other devices than desktop and laptops?
So to be honest, I actually don't know as much about the plans because we do have browsers for mobile, but of course we are not the dominant browsers on things like the iPhone. So I can't speak to the plans for something like Safari.
But when you said that the support is coming for Safari and Chrome, do you also say, like, is it going to come to Chrome and Safari on mobile as well?
I believe it is, but I can't speak for other teams at other browsers. And as far as I know, they haven't.
Because when we are saying about architecture, what machines, like you said, x86 and ARM, are there any other compilers that are going to use this Like, are you working already on any other compilers than x86
So
and
x86 and ARM are assembly languages. Basically, that is part of the browser. The JavaScript engine goes from JavaScript or from WebAssembly to any one of those assembly languages for whatever it's running on. So whatever target architectures the browser supports, that's what it supports. And that's actually independent of WebAssembly. So that would be for anything that's running JavaScript on a machine. All of the WebAssembly support in current browsers is being brought into the JavaScript engines that are already running in those browsers. Now, I can't speak to any future plans. That's something that I'm not allowed to do. Is speak to future plans of browser vendors that they have not publicly announced. But I do believe that we will have it on mobile devices. Any other questions? Go ahead.
Well, TypeScript has become quite a buzzword lately because of Angular, the third.
Right.
But it's a static language, but it only like emulates this. It tricks the programmer that he can use the static language, but it's really JavaScript.
Right.
Down below. Can WebAssembly make use of that ahead of running assumptions that we know what properties that the given object has to optimize the code better?
Yes. Well, I shouldn't say that's something that people have been talking about. The possibility of that. Now, there's still a lot of, even if you add TypeScript types, there's still some dynamism there. So you need to have what some people have been calling TypeScript ++, like a more locked down version of TypeScript in order to do that. But one of the cool possibilities that could open up is you add fully, basically you make some of your JavaScript fully static, but you do that gradually as you have time and want to make certain files totally static. Then you could compile those to WebAssembly, and the rest could still compile to JavaScript, and it would just interoperate as seamlessly as if it were all, JavaScript. So that is a possibility. It's not necessarily going to happen, but that's something people have been talking about. And almost forgot. Any other questions?
Okay. For me, as a JavaScript developer, one of the biggest advantages of JavaScript is developing tools. And I'm curious about debugging WebAssembly inside browsers. So it'd be nice if you give us a bit of this.
That's tough right now. So both Chrome and Firefox have WebAssembly debugging in the debugger. But right now, you're just looking at assembly code, like WebAssembly code. You're just looking at the instructions, which is not what you programmed in. If you programmed in C or C++ and compiled to WebAssembly. So what we're planning to do in the future is add source map support so that you would be able to go back to C or C++ or Rust or whatever languages. Once we have built-in GC support, more GC languages will also be in the picture.
It's going to happen in this year, or it's just big picture?
Oh, are you talking about source maps or GC?
Source maps.
Source maps. I honestly haven't checked in with the team to see how far that's coming. I would say probably a bit more than a year, but I haven't talked with them recently enough to know for sure. But right now, you can actually see in so Firefox's support is a little bit better than Chrome's at the moment. You can see like variable values in Firefox, which you can't see in Chrome. At least a few weeks ago you couldn't. But we're both actively working on it. And Microsoft's also working on their tools around it. I don't know about Safari. Yeah. Here you go. Sandra, should we wrap it up? Okay. If there's one last question, I could take one last question, but there we go.
How WebAssembly is working out with memory leaks in C or C++?
So, the nice thing about it is that because it's a JavaScript array buffer, the actual memory object itself, which you're writing all your bytes to, that memory object is actually just a JavaScript object that will get garbage collected as soon as the WebAssembly instance is cleaned up. So that's actually one of the cool things about using an array buffer for your memory. There's multiple reasons why it's cool, and I talked about those in my React Europe talk, and I'm going to be posting that little bit of the talk as a blog post in the coming weeks. But yeah, that stuff excites me. So, so let me see if I can get this. Yes. Thank you all.